Hi everybody, my name is David Heslom. I work here at Earth Advantage, remodeling program and energy performance score program manager. And I have taught the SHP class in the past before as well. So it's great to see such a big class. And what I'm here to do with you is show you the MAD air house. And it looks like a engineer's dollhouse, but what really is it's a tool to help you understand how things like bath fans, basement fans, attic fans, furnace fans, leaky ductwork can create different pressure dynamics within a building. So what you'll be learning in class is those different pressures can cause lots of issues for a home, from life safety issues, because if you depressurize a combustion zone, now you could backdraft on a gas appliance or an oil appliance or a wood stove. And that's not good, because when you backdraft it, that means all the exhaust gases that are supposed to be outside are inside. That's when you have carbon monoxide poisoning in a home, typically. Every winter, 1 or 2 families in the Northwest die because their equipment is backdrafting. Okay? This can help you understand why that can take place. So that's one thing. Other things to learn about have a lot more to do with the ductwork. Where a duct leak may cause high pressure in a certain part of the house or low pressure in a certain part of the house. And that can create issues around moisture. Say, for instance, if you have a bedroom with very high pressure in it, and there's a lot of moisture in that bedroom because people are breathing into it all night long. Each person's giving off at least a quart of water. If there's high pressure in there, that moisture gets driven into the building assemblies typically by small air leakage paths within your walls, floors, and ceilings. And over time, that type of moisture buildup actually can rot out the building and cause things like mold to take place, which then become separate health issues. But it actually can cause real structural damage. I've seen homes where the sheathing of the bedroom walls was actually just entirely rotted because they didn't have any pressure relief for the bedroom. Basically, they had multiple layers of carpet, a tight-fitting door, and no return air for that room. And so every time the heat was running in it, that room was positively pressured, and it forced all that moisture into their walls through leaky electrical outlets and under and around the drywall, and it rotted out their building. The building was insulated to code, but that didn't stop it from rotting out because of the fact that there was a dynamic setup basically around their ductwork system. It wasn't any other issue in their home. And we can see the effects of that with this. So what we're going to do, I'm going to we're going to test the conditions in a combustion safety zone of the house. So we got typically set up here, we have a water heater, naturally vented water heater tucked into the basement down here, which is a pretty standard situation. We've got a flue that comes all the way up and out of the house right here. It mimics a naturally vented water heater because there's a gap between the unit and the flue, and that's what you have on a standard atmospherically vented water heater. I have a manometer set up here. Does anyone know what a manometer does?
It's pressure. Measuring pascals.
It measures differences in pressure. So originally manometers were tubes of water, and in one place you had greater air pressure and it would push the water column further up in the other area. And that's why we actually measure air pressure in inches of water column. But these are all electronic, and we have 2 ports. It's measuring the difference between this port and that port. So when you do building diagnostics, say for a house, initially you set up what is the pressure differential with respect to the outside. So we have a combustion zone right here. What is the pressure differential between that combustion zone And outside, well, it ought to be 0 right now because this is a toy house set up with inside this building. We really ought to not have a difference there. And our manometer says the difference is 0. If this were the typical house, and you're thinking about how the stack effect works in the house, you've been learning about the stack effect in class, right? A little bit so far? No. Stack effect is the concept that hot air rises. So within any given building, hot air is always trying to leave out the top of the building. Because of that, as it tries to get through the ceiling, it builds up a positive pressure up there. And because within a container, like a building, if one part is positive, somewhere else it has to be negative. And that means at the bottom of the house, you pretty much always, all year long, you have a negatively pressured crawl space or basement or right above the slab. Is always negatively pressured, which means this part of the house is always sucking air in from whatever's around it. Okay? And up here, just inside this roof plane, it's always positive. Or if this is a ventilated attic, just under this insulated roof, it's always positive. And somewhere in the middle of the house, you have a neutral pressure plane. It's not positive or negative there. And, you know, if you really like to have fun with building diagnostics, you walk around your house with a manometer, and you can find out, oh, on this particular day, you know, where is my neutral pressure plane? You have to be, you know, a pretty nerdy building scientist to have that kind of thing as your fun, but, you know, that's the kind of people we are. Okay, right now though, it's a pretend house, so we have 0 as our pressure right here. But for instance, say you have a fan going because you have a laundry in your basement. So I can simulate that. For all intents and purposes, see that's the basement. For all intents and purposes, you can see the fan blowing out this flap here. So you can tell air is leaving. You know, for all intents and purposes, that could be the dryer running. Okay? That's a typical scenario in a basement. You've got the water heater right here. You've got the dryer right next to it. And then they may have put in a fan as well to help it from getting so damp in that basement area. So just by turning this fan on, we've now depressurized that basement area by 0.2 pascals. Pascals is the standard unit of measure for air pressure. That's not very much. Of course, we have a big hole in our basement right there. It's a ventilated basement. Consider that like a cat door. If you were to cover that hole up, the fan effect would be higher. You know, now it's coming to negative 0.3 or so. What you really care about when you're thinking about a worst case scenario for that water heater though is what other conditions could there be in this house that are going to make this pressure go as low as we can possibly test. What we're simulating right now is what's the worst possible case for that water heater before it turns on? How can we depressurize the basement to its absolute maximum?
Seal up the door.
Well, sealing up a door may or may not make it worse. Because
Well,
we have, what are things that depressurize houses?
fans. So you turn on a bathroom fan, like
Right.
on the second floor, or
So a standard procedure, if you're following like Building Performance
Turn it
Institute
on.
standards, you would go around and you would turn all the exhaust fans in the house on. So we have a bedroom exhaust fan I'm turning on, and I have a main exhaust fan I'm turning on. So now, just by turning those fans on, I now have increased the depressurization in there by 1.0, but we don't necessarily have much conductivity into the basement from these other fans. So I can open these holes, make sure they're all the way open, so that there is connection. And then I can also open some holes in the ductwork, which actually accentuates the connectivity around the house. I can open this door here. So now the house is all very open to itself. So we're getting a lot of airflow So the fans, where the fans are sucking air, it's able to pull all the way from down here. And now we've created a negative pressure of about 1.2 pascals.
Would a furnace have anything to do with that if it was in the basement?
Yes. So how could let's go with that. How could a furnace depressurize it even more?
Turn the fan on.
Well, you turn the fan of the furnace on. So if I'm going to, if I leave both these ducts totally open, so I have a really leaky ductwork system, and now I turn the fan on for our furnace system, does that affect, we've now gone to minus 1.4 pascals for that area. But what really will make that worse is if the ductwork is leaky on the return side, but not leaky on the supply side. Because the ductwork is down here in the basement, and if it's leaky on the return side, it's going to act like an exhaust fan and suck it out of that area. So if I close off, if I make it tight on the supply side and leaky on the return side, I get even a little more negative, minus 1.5. What I learned before you were here, actually, is if I cut off the rest of the building from here, that fan effect that we have going on with the furnace is even stronger if we cut off the basement from the rest of the house, because your furnace effects can be really quite large. You know, what's the blower size on a typical furnace? You know, you're talking 800 CFM, 1200 CFM. That's cubic feet per minute. That fan blows. You know, a bath fan moves 50 CFM, 70 CFM, 90 CFM. Most range hoods are moving, you know, it might be rated at 300, it might move 150. So the power that's in the furnace fan to create pressure and depressurization is very large. So it's a big force that you can apply to the building. So now I could even turn off these other fans in the house, and we might get our worst scenario. Nope, they're actually contributing slightly. So our very worst scenario that we've been able to create is we have all our fans running, and we have a leaky return in the basement. And we have created a depressurization there of minus 1.8, minus 1.9 pascals. And then you have to say to yourself, okay, I just established what my worst case scenario was for this combustion zone. Well, what is 1.9 good? Is 1.9 bad? There's actually tables that have been set up for standards in the industry over a long time, and I can tell you that a natural draft water heater, the limit that you can have in that area is minus 2. So we're at minus 1.9. So we're, in this test scenario, if we were just a little bit, another 1/10 of a pascal, we would now be over the limit in terms of what a worst case test could show for this and be able to leave the house in that condition.
Is that a BPI standard that you're using?
That's a BPI standard.
Thanks.
They didn't, you know, there are standards that exist in the market, and they have adopted and put in place for BPI testing. Yeah.